Is Chassis. The talk title is Learning Long Horizon Biomenu Tasks Involving Deformable Objects Manipulation. Chassis is an assistant professor in computer science and electrical engineering at Stanford University. Her research interests lie in the capability of robots and other agents to develop broadly intelligent behavior through learning and interaction. To this end, her work has pioneered end-to-end deep learning methods for vision-based robotic manipulation, meta-learning algorithms for few-shot learning, and approaches for scaling robot learning to broad datasets. Her research has been recognized by awards such as the Sloan Fellowship, the IEEE RAS Early Academic Career Award, and the ACM Doctoral Dissertation Award, and has been covered by various media outlets, including the New York Times, Wired, and Bloomberg. Prior to Stanford, she received her bachelor's degree in electrical engineering and computer science at MIT, and her PhD in computer science at UC Berkeley. Jessie, I'll hand over to you.
Awesome. Thank you for the introduction. I hope that all of you can hear me okay. I'm sad that I wasn't able to make it in person to ICRA this year, but yeah, grateful that I'll get to share a little bit about what we've been working on. And there'll also be some time at the end for questions. And so, yeah, happy to take questions at the end. I actually want to start off by kind of going back to my talk at ICRA last year. And I talked a lot about how robots can perform fine manipulation skills with difficult to simulate objects, including deformable objects. And specifically, I presented some of our work on the Aloha teleoperation system. And kind of a big part of this work was first on the hardware side, trying to develop a teleoperation system that allows you to perform a wide range of different tasks, and including tasks like being able to stuff things into a plastic bag, zip up a hoodie, and so forth. And with the system, we were able to train neural network policies to be able to autonomously complete different tasks by providing 50 demonstrations of each task and training a neural network to control the robot to do that task. So on the top right was a task of tearing off a piece of tape and putting it on a box. And on the bottom right, we were learning a task of putting a shoe on a foot. And so kind of what I want to talk about today is actually building quite a bit on this question of, can we enable robots to perform fine manipulation skills with difficult to simulate objects? But I'd like to take it one step further and see whether we can learn fine mobile manipulation skills, and moreover, being able to learn long horizon fine manipulation skills. And in both cases, we'll be looking at really difficult to simulate objects. So let's dive in and talk about fine mobile manipulation skills. Now, when we started this work, we wanted to learn mobile manipulation skills, and we actually did a project. Zipeng was working on a project with a local bot. We were trying to learn mobile manipulation. He was really interested in the kind of whole body control. And this was a platform that we already had in the lab. And it turned out that when we actually went to collect data on this platform to try to learn manipulation tasks, it was extremely time consuming to try to control a robot. And we started out with like a joystick or kind of a handheld controller or a keyboard controller and so forth. And we weren't able to figure out a good way to efficiently collect data on this platform. And so we kind of Zipeng after this was really motivated to try to understand if we can efficiently collect mobile manipulation data that would allow us to learn from that data. And specifically inspired in part by the Aloha work, he decided that he wanted to work on mobile bimanual manipulation. And the resulting system that he developed focusing on teleoperation is this system right here. It's a mobile bimanual manipulation system. And you can see him teleoperating the robot to do a fairly wide range of tasks here, but kind of basically all surrounding cleaning the bathroom. And unlike the previous system, he's able to do a wide range of tasks, and he's able to do so fairly efficiently. This is sped up such that we can just show you kind of show a wide range of things that you can do with it. But even in real time, the speed certainly isn't at human speed, but it's actually quite reasonable for teleoperation. And moreover, kind of a few things that are worth noting. First, you can do whole body teleoperation, so you can control both the base and the arms at the same time. And the arms are done with puppeteering, similar to the Aloha system. And the mobile base is teleoperated by simply pushing the base, and you can record use the encoders to record how it's moved and then command it to move accordingly. All of it is done in a $32,000 budget, which is generally kind of trying to push the boundaries on low-cost robots. And we've seen those boundaries be pushed even more so. And I think that we can probably make this system even cheaper with more recent hardware that's being developed now. And then the other thing is it's all onboard power and compute, which means that you can take it lots of different places and you don't have to be bottlenecked by like a workstation or power supply. Cool. So this was a teleoperation system that Zipeng was working on. And the motivation ultimately was, of course, to actually allow the robot to autonomously perform tasks. And to do that, he followed a very similar method as what we did in the Aloha work. We're training a transformer. This transformer architecture has both an encoder and a decoder. The encoder is taking as input embeddings from each of the images. In the original Aloha work, we were using 4 cameras. In mobile Aloha, we just had 3, one for each of the wrists and 1 third-person camera. And then these are mapping both to joint angles as well as to the motion of the base. One thing that we found to be really important in some of our prior works and also found to be important here is to predict a chunk of actions at a time and execute that chunk open loop until the start of the next chunk. And then the big thing that was that we did that was a little bit different in this mobile manipulation work was actually to co-train on static manipulation data. And we found that this, and I'll kind of, as I show in some of our experiments later, we found that by co-training on both static and mobile manipulation data, it kind of acted as a form of regularizer and allowed us to learn mobile manipulation tasks with on the order of 50 demonstrations, which in the grand scheme of things is actually quite small. So this is the gist of what we did. So kind of concretely, with the teleoperation system, you collect 50 demonstrations showing the robot how to do the task repeatedly under different initial conditions. And then we train this transformer model on those 50 mobile manipulation data demonstrations alongside static Aloha data that was previously collected, around 800 demonstrations. And then we evaluated how well the policy could do fairly challenging mobile manipulation tasks. And so specifically, here are 4 of the tasks that we looked at. These videos are all the robot acting autonomously without teleoperation. And so we studied a task that involves a lot of mobility, like driving up to an elevator, pressing the button, and entering the elevator. And we found that it was able to do this with 50 demonstrations. It was able to do this quite successfully. And this actually is quite challenging because you need to fairly precisely press the button. And if you're off by like a centimeter after navigating there, then it won't successfully open the elevator. We also looked at a task of cleaning up a spill on the table, which involved driving up to pick a towel on the faucet here, and then driving over to a spill, picking up the wine glass and pouring it. And I guess I should mention, given that this is a workshop on deformable objects, in many ways, like what we're doing here, we're not doing anything special to handle deformable objects. It's kind of the same method, and it doesn't really care if the objects in the environment are deformable or rigid and so forth. That's one of the really nice things about an end-to-end learning approach is you essentially just need to provide the data, sufficient data that can be used to train it, and the rest can follow. A third task that we looked at was pushing in a number of chairs, sequence of chairs. In this case, we actually only trained on data that was pushing in the first 3 chairs, but because it's a fairly repetitive task and all of the camera images are from like an egocentric perspective from the robot, we found that the policy actually was able to extrapolate to the 4th and 5th chair. These videos are not sped up, so maybe a little bit patient to get all the way there. But in the meantime, a 4th task that we looked at was being able to put away a pot. And for this task, you actually have to very closely coordinate both of the arms and move the base at the same time. And so this is really emphasizing the importance of being able to do a task that involves whole body control rather than alternating between operating the arms and operating the base of the robot. In the meantime, we can see that in the bottom left, the robot is successfully pushing in the fourth and fifth chair. So the success rate of these policies they're actually quite reliable, but isn't 100%. So the success rate of these are around 80 to 100% success rate in the environments that they were trained on. We also looked at one more, even more challenging task. This one, we only collected 20 demonstrations simply because it was it was somewhat time consuming to collect demonstrations. Also, the shrimp had various fragrances that were not so pleasant to collect data with. But nonetheless, despite this, we were able to get a policy that was able to succeed at the full task of cooking one piece of shrimp around 40% of the time. And I expect that if we are able to collect more data, then it would be even more successful. And so here, the full task involves pouring olive oil on the pan, then putting the shrimp into the pan, using the spatula to flip the shrimp on the pan, putting down the spatula, and then eventually serving the shrimp in into a bowl on the other side of the kitchen. This last part, it ends up being a little bit less precise. We'll see. I think it might spill some oil on the counter there. So definitely some room for improvement. But I found this rather exciting because this was the first time that I'd ever seen a robot, at least in our lab, be able to do like something that resembles a real cooking task. Cool. We also did some quantitative experiments beyond watching the robot, of course. And so one of the things we wanted to look at on the hardware side was whether or not this teleoperation platform is something that people could learn how to teleoperate. And here the gray line denotes how quickly an expert is able to teleoperate the task after a lot of practice with using the system. And the blue line is showing a person who hasn't used the teleoperation system before, how quickly can they learn how to teleoperate a new task. And on average, we find that even with just like 5 trials of experience, they're able to get fairly close to the performance of the expert on average, which is a good sign. It means that this system is fairly intuitive to learn how to teleoperate. And then separately, in terms of the policy performance, we evaluated the success rate of the neural network policy with and without co-training for variable numbers of mobile manipulation demonstrations. And first, we see that there's a large gap between co-training and no co-training, suggesting that actually co-training serves as a really good regularizer and is able to lead to much stronger performance than if we were to train only on the mobile manipulation data. And second, as we'd expect, as we increase the number of mobile manipulation demonstrations from 25 to 35 to 50, we're able to get much higher success rate up into like the 90% range. Cool. So the takeaways here are that on the hardware side, we introduced an interface for teleoperating mobile manipulation tasks, including fairly complicated tasks like cooking, cleaning, and so forth. And on the learning front, we were able to learn pretty challenging mobile bimanual manipulation tasks. We found that co-training with static manipulation data was able to significantly improve performance compared to only training on the mobile manipulation data. There's also a number of really important limitations, is I think really just scratching the surface of what we can do. On the hardware side, the robot has a limited vertical range of motion. It doesn't have a way to kind of move up and down. And so this means that it can't reach objects that are like on the ground or low down or objects that are extremely high. Similarly, the ergonomics of collecting demonstrations of this have a lot of room for improvement relative to kind of the static version of this. And even the static version has room for improvement as well. And on the software side, the policies that I showed, they're fairly performant in terms of success rate, but they were trained on a fairly narrow set of initial conditions. And so as a result, we expect this policy to work well in like the kitchen that it was trained on, under the initial conditions that it was trained on, with kind of that range of initial positions. But if we put it in a new kitchen or gave it like brand new objects or put the pot in like a very different initial position, we definitely expect the policy wouldn't be able to handle that scenario. Cool. So I'd like to transition a little bit from mobile manipulation to long horizon tasks. And specifically, everything I've shown so far is just learning a single monolithic neural network policy that takes input images and outputs actions. And for really long horizon tasks, this might not be practical to do because we might need to kind of break down the task into smaller segments and be able to provide supervision at a on like a shorter time horizon. And so for this, we're going to be looking at also at the Aloha system, but it's going to be the static manipulation system. And in principle, we did these works kind of simultaneously, but or around the same time. But in principle, you could also combine these and use the approach that I'll present here with the mobile manipulation system. And we're going to be looking at very long horizon bimanual tasks, like putting all of the objects into this Ziploc bag, which is quite challenging. I was actually a little bit nervous about this task when we picked it at the beginning because I wasn't sure if we'd be able to learn such a hard task. And one thing that is noteworthy here is that for the full long horizon task of putting all the objects into the bag, it's very expensive to collect demonstrations that cover all the different states that the robot might encounter when it makes mistakes. And so this is going to motivate actually giving supervision, not just at the level of full long horizon demonstrations, but supervision that helps it figure out how to correct for mistakes when it makes those mistakes inevitably. And so the problem setup that we're going to look at is we're going to be incorporating language to help with this, the long horizon nature. And in each kind of sub-task of the full long horizon task, the robot might be kind of following an instruction, like picking up a Sharpie, putting a sponge in the bag. Maybe it struggles to put the sponge in the bag in this case, and so we'd like to be able to actually interrupt it and give it some feedback on how to do this scenario better, like maybe to try to actually use the sponge to open the bag wider because the bag isn't very open right now, and then eventually complete the task. So this is the kind of setup that we'll consider where we want to be able to give corrections on the fly to help it perform the long horizon task. And furthermore, we'd like to be able to take this language correction data and actually use this to improve the policy by actually fine-tuning the policy with this language supervision to improve our policy and eventually improve the overall performance of the robot. So essentially, we want to leverage this language supervision both on the fly and for future improvement for this challenging long horizon task. Now, when we only have language corrections to learn from, it's a little bit more challenging to improve from it because it's not something that we can directly necessarily train a robot policy with. And so we first wanted to connect the robot behavior with language. And to do this, we're going to train a hierarchical policy with language as the interface between a high-level policy and a low-level policy. And I should mention that this is something that's been done in many, many prior works, and so this is not new in the work that we're doing. And so in particular, we'll get an observation from specifically RGB images taken from the robot's cameras. This will be passed into a high-level policy that will output a language command. In this case, the language command might be something like put the tape into the bag, or maybe rotate the tape clockwise. And then we'll have a separate policy that takes as input this language and outputs actions for performing the task, such as how it should move the joint angles of the robot. Now, with this hierarchical setup, which is in many, many different prior works, our key insight is that if the low-level policy can follow a wide range of instructions, then you can actually improve the overall system just by updating the high-level policy. And specifically, if we only need to update the high-level policy, we can do so only with language supervision because the output of this policy is in the language space. More specifically, what we're going to do is we're going to essentially just do dagger on this high-level policy and freeze the low-level policy. And so what this means is as the robot's executing, we will correct it in language, and then we can use those language corrections to to change what we want the high-level language policy to be doing. And so specifically, we'll freeze the low-level policy, we'll run the robot multiple times, we'll then intervene if we see the robot doing something wrong and give it a language correction for what it should be doing instead. This language correction is going to override the high-level policy prediction. And additionally, we're going to fine-tune the high-level policy on these language corrections to encourage the high-level language policy to instead provide that language correction instead of its original prediction. Cool. So we're going to freeze the low-level policy and fine-tune the high-level policy on these language corrections without any robot demonstration data. Cool. So we gave this kind of full system a fun name, Yell at Your Robot, or Yay Robot, in the sense that you can give your corrections to your robot and use this to improve it over time. And in our experiments, we can start with some fully autonomous, the fully autonomous system, fully autonomous high-level and low-level policies. And we looked exactly at this task of putting items into a Ziploc bag. And so on the left, you can see the language instructions that the high-level policy is outputting. And before we do any fine-tuning, we can see that the robot will make a mistake, like not being able to put the Sharpie correctly into the bag. It'll release the Sharpie, and this is then it's not able to recover from those kinds of mistakes. We find that before fine-tuning, it very rarely issues corrective commands. So here it's struggling to pick up the Sharpie, and it's just repeatedly failing to pick it up. And it doesn't help, the high-level policy doesn't actually help the robot do that. And then after fine-tuning on language corrections, we find that it's able to self-correct. So here it inserts it incorrectly. Then the high-level policy says move to the right. Then the high-level policy says put the Sharpie in the bag. It makes a mistake again. Then it says move towards me, go higher, and then put it into the bag, and is able to eventually get the object into the bag successfully. We also find that after fine-tuning, it's able to correct for grasping mistakes. So here it tells it to move closer to move to the right before picking up the tape holder. It's also able to figure out how to change strategies. So originally it's trying to put the sponge into the bag and kind of shove it in. That's not being successful. And so the high-level policy then instructs it to release the sponge and push the sponge into the bag. That's a different strategy. And it's eventually able to get it a little bit more into the bag. And then as a result of this fine-tuning process, we saw some kind of self-corrections there. We also see that the robot is better at performing the full long horizon task of putting all the items into the bag. And so this video is rather long because it's a rather long task, but we see that it successfully puts the Sharpie into the bag, then it successfully puts the tape into the bag, and eventually successfully also puts the sponge most of the way into the bag like this. And this is fully autonomous. Cool. So that was after fine-tuning with the language commands compared to the base policy. We also found that we're able to give language corrections on the fly. And one of the things that's really cool about this is actually a different task where we're trying to make trail mix with the robot. And we find that if it looks like the robot's about to make a mistake, you can actually preempt the robot with language corrections on the fly to allow it to actually prevent it from making that mistake. So it's a little bit subtle right here, but we see right here, it looks like it's trying to move the scoop into the bag. The scoop is actually a little bit too high. And so the user is actually going to override this prediction right here and instead say, move the left arm to the left to move the bag to the left, go higher, and then move the scoop into the bag. And it's able to preempt it from dumping all of the peanuts onto the table, such that it's able to more successfully put the peanuts into the bag. And then after fine-tuning, we find that for pouring, it's also able to preemptively self-correct it, where it's about to make a mistake there. It then preemptively self-corrects it to go higher and move the scoop into the bag fully autonomously. Cool. And again, those were all the qualitative results. We also measured the performance quantitatively, and on 3 different tasks, we found that just with language corrections during this kind of fine-tuning post-training phase, we saw a 20% boost in the performance of the policy. over the base policy. And we found that we're able to close a lot of the gap to using a human verbal corrections as kind of an oracle performance. We also see that there's still a lot of gap between like using a human high-level policy and 100% performance. And this suggests that our low-level policies probably have a lot of room for improvement. And by improving those, then we'd be able to close the gap further with full success. Okay, so the takeaways of this part is that you can now productively yell at your robot with this method, and the robot can improve from only language feedback without demonstrations by fine-tuning this high-level instruction policy. And then one of the limitations that I highlighted is that this relies on a very performant instruction following policy. Cool. With that, I'd love to highlight Zipeng, Tony, and Lucy, who led the works that I presented, and happy to take a couple questions.
Thank you so much. For questions, please line up to the microphones or in the chat or on the slider.
Hello, great talk as always. Two questions. One about the first half, about teleop. So, what would your advice be for developing a bimanual teleop system where you can't be co-located so closely with the robot? It seems like not being able to see exactly what's in the grippers makes teleoperating for fine manipulation much, much more difficult.
Yeah, so I definitely think that remote teleoperation, it does make it much more difficult. And I think that a lot of it, I mean, latency is part of it, but I do think a big part of it is perception, and like line of sight perception is really nice. And so I think that figuring out a good solution for getting good depth perception would be especially important. And being able to perceive a lot of the scene would also be quite important. Yeah, the other thing is if you have cameras on the wrists of the robot, that could also help get a more close-up view. And so, yeah, I think that addressing latency and perception would be the two biggest things I'd pay attention to.
Great, thanks. And on the second topic, language interruptions are great. For one reason, they seem much easier, like less work for the human. But it seems like for some of the types of mistakes you're seeing, like overriding with teleop might actually just be much more efficient and give more precise feedback to the robot. What are your thoughts on sort of a holistic feedback and interruption method that includes things like language, but also things like just taking over and driving the robot?
Yeah, absolutely. And I definitely think that this approach could be combined with something that takes over as well. And that could be used to fine-tune the low-level policy. I also think that there's probably a way to use the language corrections to improve the low-level policy as well. So definitely, I think that makes a lot of sense. And I think that probably human operators and users would probably have a good intuition for when it would make sense to give a language correction versus taking over completely. Another thing that I'll mention on the topic of remote teleoperation is that language corrections are probably something that's very easy to give remotely compared to operating the robot. And so that's another advantage of this sort of approach.
I guess it seems like there's a significant challenge with physically interrupting where the puppeteering setup is not exactly matching the state of the physical setup. So in that case, it's not clear what a physical sort of interruption and demonstration would.
Right. So one way that you can do this is if you I don't know, press a button or somehow tell the robot to stop what it's doing, you can have it pause and then move leader arms to that position. You could also have the leader arms track what the follower arms are doing, what the policy is doing, so that it is kind of doing exactly what the policy is doing, so you can actually interrupt. Probably the easiest way would be to ask the robot to pause rather than trying to like hold the handles, kind of like you hold the steering wheel if you're like in like full self-driving mode and it's kind of awkward to try to hold the steering wheel while it's doing that. So certainly there are challenges there. I don't think it's impossible with the puppeteering setup by having the leader arms track the follower arms that the policy is operating, but definitely introduces more challenges.
Great, thank you.
Hello, thanks for the interesting talk. My question about this presentation is about the first half of about the teleoperation system. I think the current system is heavily relying on the visual observations. However, given the context of this workshop about deformable manipulation, there are actually a lot of property that you cannot, that is hard to estimate directly from visuals. What do you think about addressing some of these issues in the context of learning from demonstration?
Yeah, it's a really interesting question. I've actually been surprised by like how far we can get with vision, and I think that the one of the things you can do is you can actually just like try to teleoperate the system, which only like you don't get any tactile feedback from doing that. You do get audio feedback, and so it wouldn't be too hard to attach like microphones to it. But one of the things you don't get tactile feedback, and with Aloha, we've actually done fairly delicate tasks with it without tactile feedback, such as peeling an egg, teleoperated, peeling a hard-boiled egg, and taking contact lenses out of a container, which are tasks that I would think really push the limits of what you can do without tactile sensors. That said, I do think that the certainly if we're able to get some tactile or haptic feedback back to the operator, that would probably make the interface even more intuitive and faster to use. It's definitely really challenging. But I've been, really surprised by what you can do without force feedback, without tactile feedback. And we haven't like really run into any scenarios where it was like absolutely critical and you couldn't do something without it, which is something that actually kind of surprised me a bit. Yeah.
Thank you very much.
Hi, thanks for the talk as well. One of the language commands or language corrections that parents tend to give a lot is be careful. Do you see some kind of ways to incorporate that kind of feedback as well? Because these clear instructions, of course, are very nice, and the language policies learn to, perform more fine-grained, high-level goals. But what I actually want to say is, you know these motion constraints already. Make sure you adhere to them instead of, tipping over the glass again.
Yeah, absolutely. Yeah, it's a great question. I think that so if the low-level policy is able to figure out how to follow those kinds of commands and those kinds of feedback, then I think that this same sort of approach should apply. In order to kind of be able to follow those kinds of commands, one way to do it would be to have the low-level policy receive data that kind of acts differently if you get a be careful command, like maybe it moves a little bit more slowly, it is a little bit more cautious about like staying away from obstacles or something like that. And I certainly think that it would be doable for it to kind of get some kind of understanding of this concept of being careful. As one really basic example, we found that the command like move left a little bit. We didn't collect that much. We only collected data of like moving left or like that kind of command in like some number of scenarios. And we found that it was able to generalize that concept of moving left in other scenarios. And I suspect that with being careful, it might be able to also generalize this concept of like being more cautious, moving slowly, avoiding objects and so forth. If the low-level policy had data that kind of exemplified what it's like to operate the robot carefully.
Thank you.
So I guess also on a similar note, it was very interesting work, but one point that I didn't quite get was what happens if in the process of fine-tuning the high-level policy, it starts spitting out commands that the low-level policy doesn't have experience with. So how is the low-level policy trained to make sure it'll be able to accept just about anything coming from above?
Yeah, so I unfortunately didn't get a chance to get into too much detail on the low-level policy. We train it on demonstrations, both of like kind of standard instructions as well as corrections. There are works that have focused a lot on learning good low-level policies, low-level language condition policies, and including ones that have focused on being able to generalize to a wide variety of commands. And those kinds of low-level policies are really compatible with the approach that we use here. But yeah, we were using a pretty simple approach, and a lot of it comes down to the data of like training it on both instructions and corrective instructions. The other thing that I'll mention is that, what was I gonna say? I can't remember. I was gonna say something about the high-level policy, but I can't remember. The thing I was gonna say is that the human is giving corrections, and if the human notices that the policy isn't effectively responding to some instructions, then they can also adapt and learn to not tell the robot that, because the robot isn't very responsive to that sort of scenario. So the human teacher can also adapt a little bit. And I should mention that in a lot of our experiments, the human teacher that was providing corrections was not actually a researcher, was not a robotics researcher, and so it wasn't like really an expert. And so we found that it was at least intuitive enough that non-experts were able to understand how to interact with the robot.
Thank you. Okay, thanks everyone. There seems to be no further questions, so let's thank Chelsea again.